Hello, chemists. This is Ms. Placino, and you're watching lesson 9.5 on Hess's law. In today's lesson, we're going to look at how multi-step reactions are evaluated. Hess's law is kind of an advanced topic, so if you're feeling a little confused or bogged down as we go through this lesson, forgive yourself, stay with it, keep practicing, and I promise things will start to fall into place. Goals for today's lesson. You should be able to explain what a state function is. This is kind of the heart of why we can apply Hess's law. And the big one is to calculate changes in enthalpy, also known as delta H, using Hess's law. So this will be a new way to calculate delta H. In the previous lesson, we talked about using thermochemical data tables to calculate delta H. In 9.3, we looked at using potential energy diagrams. We talked about using table I in the reference table. So this is just another tool that we have at our disposal to calculate changes in enthalpy. Calculations will be going on today, so make sure you've got a calculator ready to go. All right, let's get started. If I wanted to look at a multi-step reaction, you might kind of imagine that potential energy diagram as having like multiple hills, if you will. If we want to find delta H for the entire process, well, we know that we've got our reactants and our products. And I'm going to label this this valley or this trough I for some sort of intermediate. So we'll go through this first reaction and we'll create, an intermediate, some kind of temporary product that we ultimately want to have react again to form a new product. So if I wanted to find the delta H of this first reaction, I can look at this value right here. From my intermediate to my reactants is 1 delta H. If I wanted to get the second delta H from my intermediate to my final product, I'll call that delta H sub 1. I'll call this delta H sub 2. So if I want to find the overall delta H, most students will tell me I can take H2 and I can subtract delta H1. Be careful. Remember, whether you're exothermic or endothermic is going to dictate the sign of delta H. So if we want to find the overall delta H for the entire process, we are going to add those changes in enthalpy together. And that's really at the heart of Hess's law. I'm going to erase some of this stuff so it's not quite so messy in there. There we go. We're going to look at multiple reactions. We're going to look at their delta H's, or we're going to try to combine them so that we can ultimately get from reactants to products in a single step and calculate the delta H of that process. The reason we're able to do this is because of something called state functions. My guess is that enthalpy is a concept that is very new to you. So let's work on some functions that you might be more familiar with. We'll start with altitude. We know when you come to STI, you walk through the second floor. And let's say you got to get up to chemistry class right away on the 9th floor. You could go ahead and just take the stairs. Lots of flights of stairs. You could take escalators. Maybe you're able to sneak in the elevator and no teacher notices and you're able to get up to the 9th floor that way. Maybe you use some combination of all three. Regardless of how you get from the 2nd floor up to the 9th floor, your change in altitude is the same. You will have covered 7 floors. So whether it was all, stairs, all escalator, somehow all elevator, the change in altitude is the same. We would say that altitude is independent of path, meaning it doesn't matter how you got from the 2nd to the 9th floor, whether it's stairs, escalator, elevator, etc. All that matters is where you started and where you ended. How you got there is not important. Let's compare that to distance. We're in our chemistry classroom, 940. We know just down the hall, we have the bathroom. I know some of you, when you ask to use the restroom, you just make that trip there and back, kind of no funny business whatsoever. You can imagine I've had some students who they leave room 940 and they go over to 939 to see what their friend's doing, and they're wandering around, they're looking at the bulletin boards, they poke their head in the English classroom for a second, they go get a drink of water, They're starting to come back to the class. Oh my goodness, I forgot that I had to go to the bathroom. They stop, and then then we kind of make our way back. Distance is incredibly dependent on path. You can probably make it to the bathroom and back in maybe 100 steps or so if you are kind of on a mission, or you could make it very, very long if you just kind of meander all through the 9th floor and you don't kind of make it a there and back trip. Distance is dependent on path. So altitude is what we would call a state function, independent of path. It turns out that enthalpy has a lot more in common with altitude than it does distance. So let's try to apply this to enthalpy, and we'll do that using Hess's law. Hess's law states that because enthalpy is a state function, again, independent of path, we can take a series of reactions. We can add them together, and the enthalpy change for the net reaction is going to be equal to the enthalpy changes that we sum up of the individual steps. Basically, the whole is equal to the sum of the parts. And we're going to work on really applying this concept today. But again, key here is it's a state function. That's why we're able to add them. It doesn't really matter how you get from point A to point B, or in our case, from reactants to products. It's going to be the same change in enthalpy no matter what. So we're going to work on a problem. I think that's probably the best way to kick off this discussion. And a Hess's law problem is usually set up as such. You've got a goal equation, if you will, the one that you're trying to figure out the total change in enthalpy of. And then you'll be provided with a bunch of smaller equations, equations that we can use, hopefully, we can add them together and ultimately get to our goal. So we have lots of heats of formation here. We've got the reaction synthesizing carbon dioxide, which is an exothermic process, synthesizing water, an exothermic process, and synthesizing methane, another exothermic process. So I'm going to actually head to the notes to do this, so I've got a little bit more space to write. All right, so here we are with those same three equations and our goal equation. What we need to do is find a way to manipulate these three chemical equations so that when we add them all up, we end up with our goal equation, in this case, the combustion of methane. So we're going to go equation by equation and kind of talk about the thought process on what do I do with these equations. So let's look at equation 1. Carbon plus oxygen yields carbon dioxide. I'm going to go to the goal equation and see if I have any of those substances. I've got an oxygen on the reactant side. I got carbon dioxide on the product side. Oh, we can kind of just leave this equation alone. Because my reactants and products are on the correct sides of the equation, in particular CO2. A little bit more confusing with O2 since it shows up in multiple equations. So I'm just simply going to rewrite that. I'm going to leave out my phases just for the sake of simplicity. Phases do matter, especially if you're talking about sometimes you've got a substance like in the liquid phase and sometimes in the gas phase. We'll look more at those examples kind of as they show up, but that is definitely more of an advanced problem. Since I didn't make any changes to my equation, I don't make any changes to the value of delta H. All right. As I look at equation 2, I've got my hydrogen, I've got my oxygen gas, I've got water. Okay, oxygen, again, is on the reactant side, and over on the product side, I have 2 moles of water. This equation only gives me 1 mole of water. What could I do? Yeah, I need to multiply the equation by 2. So equation 2 should be multiplied by 2, because 2 moles of water are produced in the desired equation. And since we're multiplying the equation by 2, what do we have to do with delta H? Yeah, it also has to be multiplied by 2. Whatever you do to the equation, you do to delta H. So I've got, and you really want to line up your reaction arrows. That's ultimately going to make your life a lot easier. I've got 2H2 plus 1/2 times 2 is just O2, yields 2H2O. My sign of delta H stays the same, but I need to multiply it by 2. So I've got 285, or I should say negative 285.8 times 2. That's going to give me negative 571.6 kilojoules. All right, my last equation. I've got carbon and hydrogen reacting to form methane. Methane shows up in my goal equation, right over there. In this case, methane is a product in the given equation, but it's a reactant in the goal equation. What do I need to do? Yeah, I need to reverse this reaction. So reaction 3 should be reversed. Sorry about that. Because CH4 is a reactant in the desired equation. So I'm going to put CH4 and we'll decompose it. Make that a little bit neater. Sorry, chemists. C plus 2H2. Since I've reversed the reaction, what do I need to do with the sign of delta H? Yeah, it has to be flipped. So instead of an exothermic reaction producing 74.3 kilojoules, this will be an endothermic reaction requiring 73.4 kilojoules. Okay, so I've got all of my equations lined up. I'm going to add them together. When I go to add things together, I want to cancel out the unwanted substances that show up in the same quantity as both a reactant and a product. For example, carbon is a reactant. It's also a product. Now, one carbon, or 1 mole of carbon, 1 mole of carbon, those can cancel. Is there anything else I can cancel? Hopefully we're looking at those two H2s. Yeah, those can cancel out as well. What about the O2s? No, those will not cancel. Why not? They're both on the reactant side of the equation, so they're actually going to add together. So I'll put this in another color. If I add up my reactants, I've got 2O2 plus CH4 yields carbon dioxide plus 2H2O. If you look at the equation we've written and the goal equation, hopefully you notice that they're the same. Sure, my oxygen and my oxygen and my methane are in two different locations, but they're both on the reactant side of the arrow. That's what matters. So my goal equation and what I've come up with match. So at this point in time, I can just go ahead and add up my delta H values for the individual reactions. And I come up with an overall delta H equal to negative 891.1 kilojoules. So just to kind of recap what we did, when all three subreactions, these reactions are added together, carbon and 2 moles of hydrogen cancel out. The delta H of all the reactions are then added together, and a final enthalpy of, in this case, negative 891.1 kilojoules is calculated. This is the third time we found the enthalpy of this reaction. We looked it up in table I. It was like negative 890 and change kilojoules. We calculated it using thermochemical data to come up with more or less the same answer. And here we've done it with Hess's law, and we've calculated, again, pretty much the same answer. The small differences in the numbers are going to be due to rounding in those values. But you can see it doesn't really matter how we get there. We're arriving at, for all practical intents and purposes, the same change in enthalpy for this equation. All right, let's wrap up the notes. All right, so let's wrap up with some kind of just general rules of thumb that you can follow when you're solving Hess's law problems. You always want to set up the known reactions or those subreactions so that the unwanted species cancel out. In order for something to cancel out, you have to have the same species, whether it is a compound or an element, as both the reactant and product. They also need to be present in the same quantity. If you switch the direction of the reaction, you've got to flip the sign of delta H. A reaction that is exothermic in the forward reaction will be endothermic in the reverse reaction. The numerical value will not change. The sign will. If you have to multiply or divide to get the correct coefficients in one of your known or sub reactions, you've got to do the same thing to the delta H of that reaction. So if you have to multiply all of the coefficients by 3, you need to multiply the delta H by 3 as well. Once all of the equations are arranged properly, you can't have just, a couple of them in the right spots. Every single sub-equation or known reaction has to be kind of lined up and ready to go. Then add them all together to get the overall reaction. You'll be able to cancel out everything you don't need. And once you have the overall reaction, kind of matching the goal reaction, add up the delta H values of the individual reactions so that you can find the change in enthalpy of the overall reaction. I think Hess's law problems are actually a lot of fun. They're kind of like little puzzles or brain teasers, and it's not just trying to grind through some chemistry problems. You've got a lot of good practice problems to work on, including some really challenging ones that hopefully will make you think and kind of push you past your limits. I hope you found this helpful, and thanks for tuning in.